Assalamualaikum and a very good day to everyone. My name is Iswani bin Yusuf and together with my group members Khatib, Amira, Shahnikli and Monira, we are from group 2. Today we will be presenting the topic electric field on the axis of a ring from the subject of electromagnetism SSCP3113. So firstly, I will explain about the situation of the electrostatic based on the condition, which means the condition where the electric field on the axis of a ring. In physics, we understand that electric charge produces electric fields, but what happens when the charges are arranged uniformly on a ring? How does the electric field behave along the central axis of the ring? And also, does the field increase, decrease, or even become zero at a certain point? This topic is important because we cannot directly apply Gauss's law due to the geometry of the ring. Instead, we use the concept of superposition and calculus to determine how each small charged element contributes to the total electric field of the axis. So based on this situation, a thin ring of radius r lies in the xy plane and carries a total charge Q distributed uniformly along the ring. A small element of charge on the ring is labeled dq. Its angular position around the ring is p. Point P lies on the ring's symmetry axis, which is the z-axis, at distance z above the center of the ring. The straight line from dq to p has length r equals to square root r to the power of 2 plus z to the power of 2. The infinite small electric field produced by dq at p is dE. By symmetry, components perpendicular to the z-axis. From all dq around the ring cancel, leaving only the z component.
We used Gemini and the prompt given was create a HTML application for calculating the electric field at point P at distance z from the center of the ring along its axis of symmetry where r is the radius of the non-conducting ring. Uniform charge density is lambda, total charge is q, and it lies on the positive xy plane. And I've also asked for it to generate an image based on the picture I've uploaded and to show the formula for the calculation. After calculating the electric field, the equation simplifies into lambda rz to pi over 4 pi epsilon naught times z squared plus r squared to the power of 3 over 2, where lambda r 2 pi equals to q, the total charge. And if we input the value of lambda to be 1 times 10 to the power negative 7, z equals 0.5 meter and r equals to 0.1 meter, the value that we get is 2.1298 times 10 to the power of 3. And if we use total charge instead, where the total charge equals to 2 times 10 to the power of negative 8, then the value that we'll get is 6.7792 times 10 to the power of 2. And we find that it is equal to the one we calculated manually.
Now, I will demonstrate how our application behaves with different input values and verify that the results are correct according to the theory. First, I will put values of radius r equal to 0.1 and then I will keep the distance z equal to 0. And when I push the button E, you can see that the value of E is 0. And we can see the green error is so small that it looks like it's disappeared. And when I change z equals to 0.5 and I push the button E, you can see that we have some value of E. And you can see that this point is farther away from the ring. So the field should be weaker. We can see that the value of E drops significantly, indicating a weaker electric field. This matches Coulomb's law. The field decreases when distance increases. And if I change Z to much bigger value, I change it to 2. When I push the button E, we can see that E drops significantly and it decays approximately as 1 over distance square, just like a point charge. This confirms that the simulation follows real physical behavior.
Next, I will continue testing the application with 3 more parameters to verify the physical behavior. So firstly, I change the charge Q to a negative value. So when the charge is negative, the electric field should point in the opposite directions. As shown in the simulator, each point to the negative z directions, which is exactly what our theory predicts. Next, I change the ring radius from 0.1 meter to 2 meter. As you can see, the electric field becomes much smaller after I increase the radius. This makes sense because when the ring gets bigger, the charges are farther away from point P, so the field becomes weaker. Lastly, I switch into lambda mode and enter lambda value of 1.0 exponent negative 7. So the STML use formula Q equals to lambda 2 pi r. So with r equals to 0.1, we get Q equals to 6.28 exponent negative 8. After I click compute, the electric field is about 1.45 exponent 10. So the lambda modes works correctly.
So, for the conclusion, we are able to compute the electric field produced by a uniformly charged ring along its axis of symmetry by making an interactive HTML file using AI tools such as OpenAI, Gemini, or maybe even DeepSeek. An idea again is that symmetry helps simplify complex charge distributions. Instead of calculating the electric fields from every small charge in a ring separately, symmetry can be used to see that the horizontal components can cancel out, leaving only the vertical z-axis component. This actually gave us the final expression for the electric field, in which Ez equals to 1 over 4 pi epsilon naught times Qz over r squared plus z squared to the power of 3 over 2. This actually allows us to better understand how continuous and charge distributions behave. In the future, understanding electric fields from continuous charge distributions is important as this knowledge can be used in many areas of engineering and physics, such as sensors, capacitors, and electric field modeling. Other than that, skills of using AI to generate working applications will help in future courses and possibly in careers because it allows us to convert complex theories into simple tools that others can use. With that, thank you so much.